And even though this is, I found this to do graphics this way more convenient than the regular way. I think it should work, surely. Or not. Oh, I haven't passed the argument to. So we have this vertex position thing, and I have to pass the boss here an angle. Oh no, his position. Angle. And it works. All right. So the next one would be asteroid instancing. So this is the patch for it. We will do instancing in a way that we create 1,000 objects and we will leave them disabled, and we will enable those what we have, exactly that amount what we have in the world. So instead of having just a single asteroid, we will have an asteroid pool. And allocate many objects, and because they should have their own position, we have to require for the object specific uniforms.
Are you making 1,000 asteroids and then just turning them on?
Yes. And we don't allocate the memory for that because we reuse the same mesh. So these are just references for the same object.
So it's like instancing?
Yes. Logically, yeah. But it's not hardware instancing because hardware supports it also. Okay. We also have to modify the add to scene function because we will use it to consume one element from the pool. Like this will be the new version. We will pass the pool here, and we just take one element off from it and activate it. I mean, enable it. Then it will return the pool from the tail, the Rust thing. Okay. Add to scene. OBJs. Or yes, that's it. Oh, and we because we changed the add to scene function to deal with pools, we will just pretend that we have a pool with one element for the spaceship. Okay. And for the asteroids, this is how it looks like. No. Yeah. Okay.
I followed this right. Every time the world is updated, a asteroid is updated or added to the world.
No, it's not added. We already added them to the world the whole pool is in the part of the object, but they are just disabled.
I mean, does it enable one asteroid for each?
Yeah, you're right. So that's each frame we enable just the right amount.
Yeah. Okay.
With the right position and angle. Yep.
You said that it was not
Mm-hmm.
so if we instancing, we need to write a geometry shader? That's
Oh, there are multiple. Yes, that's the one way to do that. But GL, the most recent GLs and also Vulkan has this, dedicated draw calls for that. But so the hardware will do the instancing for us. So we use a specific API call for that. We don't have to. The geometry shader is just one option. There are multiple hardware solutions also for that. The different trade-offs. But yeah, that's right. I mean, that's a valid option to do.
what we call valid option using Lambda.
So Lambda, this is the third generation of the system. The previous one was a Haskell EDSL, and that one supported geometry shaders. This one is not supported yet, because the goal was to create a minimal viable system. Pardon?
You said there are two approaches to do your instancing.
Mhm.
You're using a geometry shader,
Mhm.
which is the
Yep.
first approach,
Yes.
or something I didn't quite understand, using a draw call.
Yeah, draw call. So there are many OpenGL draw calls with slightly differences, and there is one for instancing as well. So if
like geo draw triangle.
Yeah, yeah.
There's one for instancing.
yes,
Oh, okay.
okay, I think okay. This is the. Let's check the what do we do with the asteroid pool? So we take the asteroid pool here, and we fold it through it. I mean, no, we take the asteroids from the word, and we will transform the pool every iteration. We just will consume just one value from it, and we call add to scene, which eventually will return the pool but with one element less in it. And we collect the remaining part here, and we disable all of them. And I think that should be it. Yes. So if I restart, then we should see something. Nope. Okay. 81, 103. Turn pool. Oh yes. As I said, we have to return the remaining part of pool. Here we go. And we have two asteroids. Okay. The next, what I have is the adding the collision geometry, because obviously we have to do debugging for when we write games. So we have to know what happens in the logic. And so we use in the logic code we use just circles, but I will visualize them as spheres, and we will generate the sphere geometry from code, like Haskell, so that we have to import the GL mesh and the vector. And also, I will add the new object array for that, specifically for debug geometry, like collision geometry. They won't have texture coordinates. It's just they will just have single 3D positions, and also we have to pass the radius of the collision shape for the objects. So we have to extend the uniform cell. Let's check the part where we create the sphere. So this sphere function gets the radius, and the n says how many is the number, the amount how we will divide it. So how many times should we divide it? And I did something. So the size of the game objects come from the logic part, like with the specific size of the collision shape, but we have to match the visual geometry into that collision geometry, right? We have to scale it in a certain way. And we can do that if we measure the size of the visual geometry, and that's what bounding sphere radius does for us. So it takes a LambdaCube mesh and checks the largest, the farthest distance, the vertex from the positions of the mesh. And so that using this function, we can calculate the size of our visual mesh, and using that size we can adjust this with scaling to match to the intended collision geometry. Okay. So let's add the extra imports quick. Add the extra input schema stuff. And here comes the usage of the model scaling, what I mentioned. So I just will, this comes after the loading. What have I done? No. So we calculate the maximum radius of the bounding sphere for the spaceship and asteroid, and we store that value, and for debug reasons we print it here. What's this? Oh yeah, we pass the radius to, it's also custom for every object, right? Because they can have custom sizes. Yes. quick. And we allocate a pool for the for our collision geometry as well, because we have to use many spheres to render the collision stuff in the screen. So it works like that. We create the sphere mesh using our sphere function. It will be a 1 length long radius with this 8 division, and we upload it to the GPU. We create the pool here, and okay. Then we extend the add to scene function to accept the radius. It comes here. Float, right? And we pass it to, we update the object value, and here comes the rendering part. We will do exactly the same thing what we done with the asteroids. Like we will consume the objects from the pool one by one. But we have to distinguish between the spaceship thing and the asteroids. So we will use the sphere pool to add those objects to the scene, but we will use the positions of the spaceship and the size of the spaceship and the same for the asteroids. And we disable the rest. Okay.
How do you do occlusion culling? Is that with your like fold M method, like the equivalent that you do, so that you don't like render all of them at once?
Yeah, basically, you would calculate the mask. Which objects should you disable? That would be the same.
And how do you know this, like the size of the screen, or which ones go off screen?
For occlusion cooling, you usually use a bounding box or bounding sphere. So using that simplified geometry for that.
Do you do that?
No, it's not implemented here. But it's not in LambdaCube. LambdaCube is not an engine. It's just a language to make it convenient to describe the rendering functions. But you can build an engine on top of it. Oh yeah, and the next thing what we added the collision geometry, but we have to adjust our visual geometry to match the collision one. So we pass the radius, that will be the scaling factor, and it comes after the angle. Asteroid spaceship. Here. Right. No, I'm almost done. Here we go. I think that's it. Yeah. So I think this time we will see the same thing, because we added the models to the storage, but we haven't modified our pipeline. to consume it. So what changes here is we will have a new input, this radius, and a new set of objects, the object array, the debug objects with only the position. Then we will pass it to the make frame, like these two new arguments, and we will have a new overlay layer here. What will deal with the collision visuals. Like you can see, it uses the debug prims instead of prims, and the rasterization configuration will say it's not polygon fill compared to the other one, which is, so this is polygon line, the other one is polygon fill. This means these things will be rendered wireframe. Okay, to make it a little bit quicker, I just will copy this thing. Stages. This is 04. And I have to rename it. I'll see. And here we go. So it's just exactly the same what we did before, but we just added a new layer for rendering. And we also introduced this debug position, but it's exactly very similar to the vertex position and texture. The difference is the set of arguments and how it. The first one returns a UV coordinate for texture mapping. The other one just calculates one four-dimensional vector, like if you see the n type, the result type. Okay, let's move. The next one will be background, adding a background, but to that we have to add another layer. So background can be drawn in a way that, just imagine we draw a rectangle what matches exactly the window, and if we do a texture mapping on it, then we can draw whatever background what we want. So that's the plan to do it. Oh, I forgot something. So we visualize the collision for our game, but I didn't turn on the collision detections in the logic. But I do, because I deliberately disabled it in the beginning. So there's two functions. One was the step word, and the other is the collide word, which types is just consumes a word, and in monad random it generates a new one. It might introduce new asteroids or particles. So if I recompile now, then I actually can die with the spaceship, and also can yes, boom. So our collision shapes are accurate. Don't you mind if I just speed up a little bit, because the few things are remain. I will add the background, also bullets. I mean, just to let the game shoot, and we will have a particle system and a post-processing in the end. So just some of them are kind of similar that we did before. So just move to the interesting part. That means anyway, I can show the patch files for those that will explain. So for background, we will use juicy pixels, and also we'll introduce a new object array which will contain exactly one quad, what will cover the whole screen. And that quad will have the 2D positions. It won't be a 3D, just a 2D quad which covers the screen, and also a UV coordinate for the texture mapping. And we upload the quad to the GPU and also put it to this quad slot with the custom object uniform, this diffuse texture, and we will load our background image and upload to the GPU. And at this point, we will just set the quad's diffuse texture value. That's the Haskell side. Or no, and we also define the quad like just a regular mesh with these values. Simple. For the pipeline part, we will get a new input, the quad prim, and also we will introduce a new layer, what will render the quad just before the collision geometry. So this is what's gonna happen if I copy. Yes, and also the HS, or I can, actually I can, not for convenience reasons, I copy it as well. Okay. What? Missing quad. No, well, I'm in trouble. Okay. That means when we quad, so when we pair the storage with the pipeline, we just got the error message that there is no quad. But that's interesting because there is. No, so the error comes at the point when we call this the set storage, and it checks that the pipeline has a slot for quad, but the storage doesn't at that point. Quad UV. Let's see, I haven't seen that it was recompiled, so just to make sure it works now. Oh, I got it. Oh, that's better. I know what's that. So we have the background rendered using a quad. The next is adding the rendering for the bullets. And we don't even have to touch the LC part, the pipeline part for that. So what we do is just load a new object, calculate the bonding sphere for that object, just to to scale to the collision shape. Also deal with the uploading the material data, do a pool for the bullets, and use the pool to activate the objects from it, and also render the collision geometry for the bullets. That these are the parts. So we've seen this before. And so now we can shoot, and the game logic kicks in and breaks up the asteroids. Just one more thing. So maybe the collision geometry is kind of annoying. Let's disable it for temporarily. We can do that if we comment out the relevant part from the pipeline. Like it's this one where we consume the debug prims, and if I go back, it disappears by the time, because it's a check that the pipeline changed and reloaded it. Okay, that's not bad. Let's improve the visual a little bit by adding particles. Particles will be just 2D things. For that, we will add another object array with 2D positions and 2D UVs, and particles will have lifetime. Obviously, what we need to do is load the particle texture, upload the GPU, create the particle pool, and also we will need a new utility function, this add to scene 2D, which will consume a particle from pool each time we call it, and set up the instance variables like the lifetime, radius, position. And we have to go through the particles that come from the word, so it's game logic creates for us. I mean, that's the logic part. We just iterate through it and set up for graphics. Regarding the LambdaCube part, something new is coming. This is the first time we were going to use blend functionality, because blending is for doing transparency. It will do additive blending, so it's pretty simple. So this is the configuration for the blend operation, and we will use this blend here. So we will accumulate the pixels or the fragments, but this time we will use you don't use no blending, but we will use actual additive blending. That's the only relevant difference comparing the previous things. All right. So but the particles has lifetime, and we use the lifetime to make it more transparent in time. In terms of code, it looks like so. This is the layer where we deal with the particles, and this is the fragment shader, which does the texturing, but we multiply the texture value with the minimum of the lifetime, or 0.4. So when the lifetime drops under 0.4, it just gets more transparent. That means actually, okay. So it looks like this. It's kind of better than nothing. Okay, then only one thing remains, the post-process thing. It's in LambdaCube we can render to texture, like the whole frame what we see on the screen we can put in a texture and reuse or render it in the next in another layer, render it to the quad and put that to the screen. And while we render that, we can alter how we sample the pixels from the texture. Like we can distort it. For example, if we define an offset texture, like this one, this contains three-dimensional vectors that can be visualized as a color image, but it's actually just a normal map. So anyway, what we're going to use is this texture to give an offset to our texture sampling. And the patch for that looks like this. We add the new uniform, what we'll refer to this distortion texture. We upload the distortion texture to the GPU and introduce this post-process function into the pipeline. And the interesting part is this one. This post-process consumes an image and produces an image, but that image can be loaded from the previous so this could come from a texture or can come from the rendering buffer, right? What we rendered on the screen. Okay. So just a quick one to show it, how it works or what it does. So what we do is this post-process will sample. So we render a quad to the screen. In the end, this post-process uses this quad primitive, which covers the whole screen, and there's only just one texture sampling in this line. It distorts the incoming UV texture with this distort function, which is this one. But that value is basically the offset value in the distortion texture, what belongs to that position, right? So if I run the program again, I can disable it. Obviously, it will disappear. Or I can even apply it multiple times. Like, or, oh yes, I have to use project image in this case. So this is compositional, just function composition, basically. Okay. Do you have questions? Sorry for being that boring, but anyway.
So, you said that previous version of LambdaCube, now it's a different language with singletons and vector coding, which seems to me like very minor additions. Can you explain the motivations for creating a separate language?
Yes. The type system is kind of different. It targets a heterogeneous architecture. That means some parts of the program that we write in LambdaCube will end up being in the CPU, other parts will be in the GPU, and I make annotations on these types, which tags where this expression belongs to. And GHC targets a homogeneous CPU, basically, with heap, or, yeah, with that memory model. So this is a different machine model, and it was more convenient to write a custom solution for that, because it's more convenient to experiment with.
And are there examples of those types?
Okay. In the DSL, the current version doesn't have that sophisticated types yet, but the EDSL version was a big GADT which had the EDSL AST, and it has a type variable what encoded the stage of the GPU, where it's run, and so the DSL is a kind of still work in progress, and the EDSL had more features, but there's another opportunity with the DSL. We can give domain-specific error messages, but it's not done well yet. But my other motivation, I have other motivations as well, but that's not graphic relevant. I also just interested in comparison in general and want to add different backend for the system. So this is kind of Haskell, but applied for a different field, and I really don't want to deviate from the Haskell at all, because I like it. I have no problem. I find that the GHC is just too big to experiment with, and yeah. Maybe I haven't answered the question correctly, or?
No, I think so. If I understood correctly, the representation
Yes.
the types where they run, that annotates the types, but I assume that currently they look a lot like the Haskell types.
I can show the types here if it runs, but I think the firewall prevents it. So the system, LambdaCube, has a web page with an online editor where the types are actually shown if you move the mouse over the source code, but it doesn't load because the firewall thing. Aside that, what am I doing here? I can show the built-in. So the system has type in type inside it. So that's how the constraints are encoded. So it's dependently typed, basically, the language inside. But the dependently typed part are applied only for domain-specific parts. So I use the type calculations to ensure that the constraint holds. It's not for generic programming. It's not exposed to the front end. But the inside of the system is dependently typed. And it also has type inference, so it's a kind of mixture of the words here. Okay, and to show the back. We can. So these are the internals of the LambdaCube, I mean the prelude and the built-ins. I try to find the type as an example. I think it will be the built-ins contains the domain-specific part of the system, which comes from the hardware restrictions, and like these are the primitive operations what can be generated as a shader. If it would be EDSL, it had an extra constraint what restricts the stage, but it's not done in the DSL version of the system yet, but it will be eventually for sure. Anyway, but this is more interesting if you are a compiler developer or dealing with type theory or type inference or whatever. So this system is a combination of these two words. Like I really like this compiler thing and the theoretical stuff, but I also want to apply it for on something realistic or practical. And I do it because I think it's feasible to have a real performance system and also being that high level.
The only functional graphics programming language currently that you know of?
Yes.
Yeah.
Only pure. There are others, but they usually do the draw call things in an imperative way.
Are there any games that are freely available that you can try out that are made with this engine? Or
I have another side project. It's I built a Quake 3 map viewer using LambdaCube, and actually I can show it. I think it's compiled. I use so Quake 3 has a shareware, the demo versions, and that game content is available for free. So I use that game content. I think it's stack. Exact. Should be like this. TM. Let's go with this one. At first, it just loads a debug pipeline because it compiles a pipeline for each level. It reads the material description, the graphics description for that level, and sends the description to the compiler, and it returns the compiled description, which is replaced on the fly with. So this is a different project. My goal here is to create an actual 3D game in a purely functional way only, and should be performant as well. Sorry?
This brings me back.
The collision detection for Bezier curves are not done. So this is the debug pipeline, and this is a runtime hot switch. Like I have both pipeline connected to the same storage, but it's up to my application which one do I use for rendering.
You have a mesh-based collision detection. What do you use to collide with your character?
Quake doesn't have that. It has a trace base. It basically the static geometry, the map is accurate triangle. Every triangle, actually, it's something called brushes, and it's a set of two-dimensional spaces what defines the collision volume. And there is a ray casting, like ejecting ray traces that checks the collision. Anyway, my system can load the animations, but the game logic is not done yet. But this is just started as a map viewer at all. I gradually added more features, and like jump pads work partially, and also there's a Flappy Bird style thing, and the teleports are working. But the code was really horrible, so I started to refactor, and luckily in Haskell you can do it easily. So the nice version doesn't have that many features, but the code is actually really nice. It doesn't have gravity yet, but you can pick up items. Like we will see, it will come back later. I mean respawn. Just have to wait. Okay. And we can shoot, but the compiler is kind of slow. So and it also doesn't pre-caches certain materials. So that was the first time when I first shoot, it had to recompile the pipeline. That was why it got stuck. And also, anyway, so if you're interested, you can find this repository on LambdaCube GitHub. I mean the LambdaCube organization GitHub, and it's LambdaCube Quake 3. It has a nice description of how to compile it. Like if you click to this image, it also brings you there. So there's a install manual for it.
How does the performance compare to what's written?
Okay, good question. It's slower than that, but it doesn't even reach the possible limits. The theoretical, not even the practical limit haven't reached that. The thing is, the compiler is too stupid at the moment, and I don't have to touch the application side at all. Only thing what I have to do is to introduce. I already checked which optimization, so I have to introduce the optimization in the compiler just to compile a different pipeline for this description. At the moment, the problem is that whenever a material has a unique unique texture, it will have its own shader program. So, and there are obviously many textures in the level. So there are 300 shader program changes in every frame, and it's pretty bad. But it can be solved if I would introduce as a parameter to the shader and pass it as a uniform value. So that's the optimization about the transformation what the compiler should do. And in that case, this would speed up, I don't know, 10 times or something. So to me, this is kind of interesting because I can make a program faster not touching it. Right?
What are your future goals for LambdaCube? Besides the optimization you mentioned, what do you see going forward?
Um,
What do you see as your goals? What do you see as your future 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 goals? What do you see as your fu
I'd like to build some game with it and store it and sell it to App Store or something, Google Play, to explain how it can be done multiple ways. Like there is only way that, so there is one way where we just describe the graphics part in LambdaCube and do the rest in like Swift for iOS or whatever. And it's possible because our application is not tied to LambdaCube. So we have the compiler, it compiles the graphic description, and we implement our application logic in our native language on the platform. And we just use a library in our project what will deal with the pipeline description. And there is already a C++ interpreter for LambdaCube. So my plan is to actually I want to use it for something because it's kind of convenient to work with. But obviously it's an early stage, might be unimplemented features or bugs, but mostly unimplemented features. But the concept definitely works. Okay. So that was it.
Thank you.